Hi all. Today we are going to learn about difference between the kilowatt and KVA. To understand that, first we need to understand what is leading and lagging phase. Let us assume that V is the voltage waveform and A is the current waveform. And even before that, we need to understand that the race is on this left side. Race is on the left side. So in this case, A is leading B, that is current wave is leading voltage wave. That is what we will say. Similarly, B is the voltage wave, A is the current wave. So in this case, current wave is lagging the voltage wave. Current wave A is lagging the voltage wave. And third scenario is A and B in the same phase, zero phase difference. Now, this is current leading, this is current lagging, and this is same phase. Now let us understand how to define this in power triangle. This is represented, this arrow represents when it is no phase difference, voltage and current in the same phase, that is active power. V into I, or I square I, when it is in the same phase, right? So when it is in the same phase means there is no phase difference. Generally this is represented by phi, not theta, but let us understand it for our understanding sake. So uh, when there is when their voltage and the current in the same phase, it means this phi or theta is zero. So cos 0 equal to 1, it means P equal to S, which means active power becomes the apparent power. And when there is 90-degree gap, when there is 90-degree gap, how much is the active power? Cos 90 equal to 0. So active power is 0, right? That is representing whether current is 90-degree lead or 90-degree lag. Just before this slide, current is 90-degree lead or 90-degree lag. This is represented by this line. So if you put uh, 90-degree here, it means cos 90 is 0, so active power is 0. Sin 90 is 1, so reactive power is Q equal to reactive power is S, means this is S is reactive power. So these are the two extreme scenario where this is active power when voltage and current in the same phase, and when voltage and current in the 90-degree difference, it is a reactive power. Active power is represented by Vi cos phi, S equal to V into I. So Vi cos phi, and reactive power is represented by Vi sin phi. This much you have to remember. Now, apparent power is the derivation of these two. If you apply the Pythagoras theorem, so this becomes the apparent power, which represents only V into I. This this is this arrow is upward because in this case the current is leading the voltage. So this is the case where current is leading the voltage. Current is leading this voltage, right? And another case will be like this, when current is lagging the voltage. This is where current is lagging the voltage. So when current is lagging, this is how it is represented. When current is leading, this is how it is represented. Now, I hope you have understood what is active power, what is reactive power, what is apparent power. Current in the same phase, current is leading or lagging, and this is the derivation of these two things. Pythagoras theorem, simple. Well, when I was studying this stuff, there was a confusion. Okay, fine. Mathematically, that is fine, but what it is actually, what it is physically. So, any electrical circuit can be comprised of three things. One is resistance, one is inductance, and another is capacitance. So, these three things represents any electrical circuit. When current is passing through this resistance, it gives I square R. That energy is can be converted into heat, can move something like when we are giving supply to a motor rotates. That's energy become that's an energy, that's an active power that we call active power. But at the same time, that motor is also generating magnetic field. That is the L component is doing that thing. That magnetic field is generated by this L component of the uh, motor. Similarly, there are cables. Cables do have capacitance. Even in this motor also, there are insulation that is representing capacitance. So this capacitance creates electric field, the charges, the electric field. But these electric field and magnetic fields are not required, which is an wastage. So uh, this can be reduced using your capacitor banks. For example, if this phi, if we can reduce it to zero, to this value, into where voltage and current both will be in the same phase, then I don't need this apparent power, and I can make this reactive loss completely zero, which is helpful for equipment sizing. For example, the transformers KVA can be reduced up to this. Transformer generators are all rated with KVA because we don't know the load which are to be driven by this transformer or the generator. If the load are lagging load, inductive load, then in that case high KVA rating is required, higher transformer size is required. But if we can mitigate that, then we can reduce the transformer size up to this only. That is the advantage we can get. So to do this, there is an entire separate arrangement called power factor correction. That is a completely separate equipment, and if you want to know about it, you can write it in the comment box. What is power factor correction and about this arrangement and equipment? More or less, this is what I wanted to tell. So active power, which is V and I in the same phase, reactive power when V and I in 90-degree separation, 90-degree phase shift, and apparent power is the derivation of active and reactive power. Simple Pythagoras theorem. And mathematically, it is V into I. This is Vi cos phi. This is Vi sin phi. Uh, that is more than enough as a beginner. If you want to know more about this or any other doubts you want to clear, you can write it in the comment box. I will create video accordingly. Thank you.